Right. So today I will continue to address the second half of chapter 8. So the first topic will be the strong law of large numbers. All right. So let me write down the statement of the strong law of large number. Okay, now we have a sequence of IID random variables. Okay, and each random variables in this sequence has a finite mean. Okay, mu. Right, so mu will be the expectation of x sub I. Right, so that is the premises. And then with probability 1, okay, with probability 1, the sample mean, okay, the sample mean up to time n, okay, well, goes to their mean, mu, as n goes to infinity. Okay. All right. So the sample mean, this is a function. Okay. Remember, it's a function from the sample space to the set of all real numbers. So this function, well, goes to a constant as n goes to infinity with probability 1. So that means that there exists an event omega 0 with the probability of this event is equal to 1. So there exists an event which occurs with probability 1. Okay? Such that for each outcome in this event, all right? So if for each outcome omega in this event, now we form this arithmetic average, okay? All right, and so now it becomes to a numerical sequence, all right? And this numerical sequence converge to mu, okay? As n goes to infinity for all outcome in omega 0. Okay? So the meaning of with probability 1 means that if we restrict the function, this function, all right, to omega 0, then this function will approach to the constant function, all right, as n goes to infinity. All right. Okay. So now All right, and in here, we will supply a proof under a more restrictive condition that if each x of I, right, if x of i's have finite force moment, or force central moment, I'm sorry. Okay, central moment is expectation of x of I minus its mean and raised to the fourth power. Okay, so if we further require x of I to have a finite force central moment, then we will give the following proof. Okay, of course we can give a proof, all right, of the strong law of large number without this more restrictive condition, but it is more involved. So in this semester, we will just give a version of proof under this more restrictive condition. Okay. All right. So so we let y sub I equal to x sub I minus mu. Then expectation of y sub I. So the force moment of yi is equal to the force central moment of x sub I. Okay, so now we know that it's finite, and which implies that the expectation of yi, okay, is finite, okay, for all k less than equal to 4, okay. By maybe we will say by a lemma in chapter 7, okay, in chapter 7. So if we have a finite high order moment, then all lower order moment were also finite, okay. So that is the idea. All right, so now we let Sn to be the partial sum of yi, okay, up to n here. And consider, so now we consider so we consider the force moment of x sub n. Okay, and now, so the force moment of x sub n can be regarded as the square of Sn square. Okay, now Sn square. So when we square this sum, then we will have the sum of xi square plus sum of cross product, all right, xi xj, And here, I will be less than j. All right, so we multiply by 2. Right. So this summation is just the square of xn, and we take the square here. Okay. Okay, and then we expand again by squaring. All right, by squaring. So the squaring of 2 terms. So this is becomes 2, the expectation, and the bilinearity of the expectation. So we can write down, well, summation I from 1 to n, expectation of xi's fourth power, plus okay, so plus the 2, so the square of this. So we have 2 here. So maybe I okay. All right. Maybe I do it step by steps. So here we have summation 1 to n. Okay. And s of I square. Okay. And here, so 2 times 2 is 4. Okay, summation I from 1 to n, xi square. And summation 1 less than equal to j, less than k, less than n. And xj, sk. Okay? This is the cross product term here. Okay. And then the squaring, so it will be 4 of the 1 less than I, j, and xi, xj square. Okay? Now, this product can be expanded. So this is actually equal to I1n. So xi square, right? Plus 2 to 1 less than I, less than j, less than n. And the xi square, xj square. Okay. So this is the square of this sum. Becomes to these 2 sums here. Okay? To this sum here. So by the linearity of expectation, now we have expectation of xi. Oh, by the way, I'm sorry. Y, not x. Sorry. So this y. Okay. Y. Okay. Y. Sorry about that. And so the sum here becomes y sub I. And here would be 2 times and the expectation of yi square, yj square. Okay. And here we can so well, okay. So the sum of these 2 because they have the same factor 4, right? So the sum of this one and the square of this, okay, this is indeed equal to okay, let me, all right, so, okay, 4, probably I will, okay, and the expectation of yi and yj, yi square, all right, yj and yk here. Okay, come here. And the last one is, so if we do the expansion, so this is 4, and expectation, summation of 1 I, j, n, summation, and k, L, n, and expectation of yi, yj, yk, and yl. Okay, right? So because when we expand, this is the squaring, right? So that the one, so this is the product of these two sum becomes 2 here, these terms. Now, let's look at this expectation. Remember, since x of i's are independent, okay, so yi's are independent too, okay? So yi are independent because that yi is a function of x of I, all right? And, okay, so, so now look at here. In here, j and k, right, are different, right? J and k are different. J and k are different. And but I can be different from j, k, but I may be equal to j or may be equal to k. Okay. So, but anyway, that so this is this expectation. All right. So we check one by one. But so we check here that expectation of yi square yj yk, right? Okay. If I, j, k are different, all right, if I, j, k are different, then yi square is independent, yi square and yj and yk are independent random variables. So we know this is become 2. Okay. If I, j, k are all distinct. Okay? The reason is that yi's are independent. So let me say yi, I, 1, 2, up to n are independent. Okay, so if I, j, k are distinct, okay, indices, then these three random variables are independent, and so the expectation of their product becomes to the product of their respective expectation. But if I equal to j, okay, of course, but as we know here, k are different, right? Then in this case, we have yi and the expectation and yk. Okay, so we have the third moment of yi times the first moment of yk. The other case would be j equal to I. So we have E sub yj. So maybe I write j here. Okay, and the expectation of yk. All right. So there are only three possibilities here. Okay, there are only three possibilities. All right, and by proposition, in the 7 point, let me see, we prove such a property in okay, 7.2.8. Okay, all right. Now, but as we know, since expectation of E sub I is expectation of x sub I minus mu, which is expectation x I minus mu, and it's mu minus mu is 0. So we know each y sub I has 0 mean. So that expectation of yi square, yj, and yk, which is 0. Okay, so all the terms here are zeros. Okay, so they are all zeros. Okay, great. Now we consider this double sum here. Okay, so consider this double sum. Okay, so furthermore, okay, the expectation of yi, yj, yk, and yl here. We only know that I is less than j and k is less than l. Okay, but it's possible that I equal to k. Okay, or I equal to l. It's possible, or j equals k or j equals l. Okay, it's possible, but so so there are some possibilities. So we have expectation of yi square, and maybe I use k. Okay, yi square and yj expectation of yj square. If I equal to k and j equal to l. Okay. Right. So in this case, that we have this expectation. Oh, sorry. Okay? Now, but if I equal to, so I equal to k, right? So if I equal to k is possible. Okay, and JKL are distinct. Okay, then we have E sub Yj, expectation of Yk square, and expectation of YL. Okay, it's here. And some other case, if I equal to L, so if I, so K, listen, if this is the case, then we have expectation of yi square, expectation of yk, yj, sorry. Expectation of yk. Okay. Okay, then the other case, so this is about I equal to m, and about j. So if I less than j equal to k less than L. Okay, in this case we have expectation yi, expectation of yj square, and the expectation of yl. Okay, and the last one, I think I have. So if j equal to L, and I jk are distinct. All right, so in this case, we have EYI, EYJ square, and EYK. Okay. All right, so you can see that except this case, the other four cases, right, has a first moment of y sub I. Okay, so you can see we have a first moment here. Okay, first moment, and the first moment of y sub I, and we know first moment of y sub I is equal to 0. So that you can see, except the first case, the other four cases, you get a 0 expectation. Okay, so we can gradually simplify this sum. Okay, so that the first moment of x sub n, okay, becomes to, okay, can be simplified to be the summation of I from 1 to n, expectation. So it's the first moment of y sub I. Okay, plus 2 times the 1 less than I, less than j, less than or equal to n, expectation of xi square, and And again, this term can be written as x of I. Sorry. Expectation yi square, expectation of xj square, yj square. Okay, because yi and yj are independent. Okay, so right, so here, and this is 0, right? So we know this one become to 0, and this one becomes to 4 times expectation of only this one. So this yi square, yj square. Yeah. Okay. So we have 4 of 1, and then I is j, so n expectation of x of I square, yi square, sorry, I square, expectation of yj square. Okay, now, because x sub i's are identically distributed, so y sub i's are also identically distributed, okay, because they have the same distribution and go over the same functions. So okay, so we can write down by using y1, the y1 as a representative random variable. So we have n times the first moment of y1. Okay, and here now, so that they have the same second moment, right? And so 2 plus 4 is 6. So 6 times. And how many pairs do we have? Ij pair, I different from j in between. And so this is n select 2. Okay. And the times, so we have e y1 square and square. Okay. Right. All right. So so this is n, is the first moment, plus 3 times n times n minus 1, and expectation of square and the square. Now, since the okay, so okay, since the variance, okay, now we use the variance of any random variables, okay, will be greater than or equal to 0. But the variance of y1 square is actually the the second moment of y1 square. So that would be the fourth moment minus the expectation of y1 square and take the square. Okay. So from here, we know that the first moment is greater than or equal to the square of the second moment. Okay. Right? So from that, so we have the square of the second moment of y1 is less than or equal to the fourth moment of y. And then, if we apply to here, then the fourth moment of the partial sum x sub n will be less than or equal to n plus, so will be less than n e y, the fourth moment plus 3n n minus 1, and here we replace this square of second moment to the fourth moment, okay, and become to an upper bound. Okay, and so we have the number is 3n squared and minus 2n, and okay, so this is the first moment of y1 here. Okay, all right, so we have this upper bound. Now, so which implies if we consider the first power of this is sample mean, okay, divided by, and so we have, so this is equal to n to the first power, and the first moment will be less than equal to the first power of n 2 minus 2n. Okay, and y1 first power. So this is upper bound bounded by so this is okay. So it's upper bounded by this number. Okay. Okay. And then, so the expectation of the series sum. Okay. So. Okay. So we consider the series sum of this positive or non-negative random variables. And as we know, because this is non-negative, so that the expectation of this series sum becomes to the series sum of the of the expectation of it, of the terms here. All right, and then we apply the upper bound here. So the bound is 3 here, 1 over n squared. Okay, and so this bound, you can see that because this series sum is finite. Okay, so this is finite. Okay, so you can see the expectation, right, of this series sum is finite. When this is finite, so therefore, right? So therefore, the probability that summation and okay, so this event must be equal to 1. Okay? Right. So that this random variable should be finite with probability 1. Probability 1. Okay. Otherwise, all right. So if this is not so if this is this event does not occur with probability 1, then otherwise the expectation okay will be greater than equal to times the probability that equal to infinity. Okay? And this will be, so otherwise it means that this probability, okay, is positive. And so positive times infinite becomes to infinite. Okay, so that means that if this is not true, then this means that the expectation of this series sum is infinite. So this is a contradiction. Okay, so this is a contradiction. So that with probability 1, right, with probability 1, that this event occur. Right. So okay, and so we let omega 0 to be the event okay, then we have the probability omega 0 is 1, and for all outcome in omega 0, we know that okay, okay, that omega is finite. Okay, so that is the definition of omega 0, right? So this is finite. All right, and so for all this, and which implies that the limit as n goes to infinity, the n Sn omega first power is equal to 0. Okay? Okay, that is from calculus, right? Okay? And so this implies that the limit n goes to infinity is n omega, and it's equal to 0. Okay, equal to 0. So you can see that we can find an event omega 0 which occurs with probability 1, such that for every outcome in this event omega 0, this sequence goes to 0. But what is that? But what is that? This is exactly divided by n, it's 0, right? And this is i.e. the limit x1 omega plus x2 omega plus xn omega divided by n minus mu equal to 0. Okay. Okay, and we have done. Okay, so this is the key result of the strong law or large number, right? So that the partial sum, okay, will approach to their mean as n goes to infinity. Okay, for every outcome omega in an event omega 0, such that this event occurs with probability 1. Okay. Okay. Another version of a strong law large number. So I will state that as 8.4.8. So the strong law of large numbers. Okay, for uncorrelated random variables. Okay. The standard or the standard strong law large number require that our sequence of random variables are independent and identically distributed with a finite mean. Okay, and this version of strong law of large numbers require only uncorrelated random variables. All right, so here we have a sequence, okay, of uncorrelated random variables. Uncorrelated means that the covariance of x sub I and x sub j, okay, is 0 for all I not equal to j. Okay, all right. So we have a sequence of uncorrelated random variables, right? Uncorrelated. And we know from chapter 7 that if this sequence of is independent random variables, all right, so if this is a sequence of independent random variables, then independency will imply uncorrelated property here. Okay, so uncorrelated random variable is a weaker condition. All right, than independence assumption here. Right, so this is weaker, but we have to pay a price for this weaker condition. Okay, so that we impose other restriction such that there exists a constant m, right? Or maybe I can, because I use such that. So I change a phrase. So such that for some constant m, the second moment, right, of x of I is less than m for all I. Okay, so the price paid here is that would require the x of i's has second moment, finite second moment, and all the second moment of x of I has a common upper bound m. Okay, so this is the requirement. So you can't have a sequence of uncorrelated random variable and such that the second moment become unbounded. All right, so that they should have a common upper bound here. Okay, so compare with the standard strong or large numbers, because the standard strong or large number does not require x of I has second moment. Only finite mean, finite expectation will be enough. Okay, but for this version of strong or large numbers, because we only require uncorrelated random variables, so that we ask for that every x of I has finite second moment, and all their second moment has a common upper bound m here. Okay, so then the limit of I from 1 to n, the x of I subtract their mean, okay, right, and then divide by n. Okay, so you subtract their mean, all right, and then form the partial sum, and then divide by n. So this is the kind of sample average, okay, but has been adjusted with respect to their mean. Okay, then so this ratio, okay, this ratio will goes to 0 with probability 1. Okay, all right, this ratio. In our standard strong or large numbers, because that they have a common, they have the same mean, so this is mu. Okay, so this is mu. So we can just replace this expressed by the common mean here. Okay, but okay, and so that means that i.e. there exists an event omega 0 such that this event occur with probability 1. Okay, all right. So such that if we form for each outcome in this event omega 0, if you compute this real number, okay, and for each outcome omega in this event capital omega 0, and this is go to 0, okay, so the limit is 0 for all outcome in this event omega 0. All right, so this is another version of strong law or large numbers. Okay, this version can be very useful, in practice. Okay, because many situations that you can justify that a sequence of random variables are uncorrelated. Okay. And then you inspect whether this is true or not. If this is true, then you can apply these versions of strong law or large number. Okay? And the proof was, so we will not give proof, so will be omitted. All right, so up to now, we have addressed the weak law of large numbers, the strong law of large numbers, and the central limit theorem. And we also mentioned some variants of these important theorems. Okay. And the last topic in this chapter will give you some useful inequalities, okay? Which can be used to estimate the probability of some interesting event, okay? Especially the tail event of a random variable. Okay. So other inequalities. Okay. The first one is about one-sided Chebyshev inequality. Okay. We have given two-sided Chebyshev inequalities in a previous section. Okay, so now X, a random variable with mean 0, so with 0 mean, okay, and finite variance. All right, so suppose we have a random variable. We know its mean is 0, and it has finite variance sigma square. Okay. Then, okay, for any a greater than 0, right? If we want to estimate the tail event of this random variable, so we want to know the probability that this random variable has value greater than or equal to this a. very often A is a large number, so we want to know the tail distribution, okay, of the random variable x. Then we have an upper bound, and this upper bound can be expressed by the variance of this random variable x and also A. Okay, so it is this one is the sigma square divided by the sum of the sigma square and the A square. Okay, so if A is quite big, it's quite big, you see that this number is very small. Okay. All right. So now we will derive this upper bound, okay, in the following way. So we let b greater than 0. Okay. Then we have, okay, the following observation. Okay. So this event, so the probability of this event is actually the probability of if we add b on both sides. Okay, so we add b on both sides here. Okay, and then the probability of this event, okay, is smaller than the probability that if you square both sides. Okay. The reason is that okay, so since x omega plus b greater than equal to a plus b, if this is true, so maybe I was calculated an outcome in this event. Okay, an outcome is in this event implies that x omega plus b is greater than equal to a plus b. And this implies that if you square both sides, and remember, this is positive, both. Okay, both are positive. Because if a plus b can be negative, okay. For example, if the sum is negative, for example, it's -5, okay, and this maybe -3 is greater than equal to -5, right? And when you take the square, the square of -3, right? It's actually, this is incorrect, right? Cannot, right? This is incorrect. So that our previous assumption is that A is greater than 0, B is greater than 0, so A plus B is positive, okay? And so this is positive. So that if we square them, we can keep the order of the direction of the inequality, right? So this is important observation, right? Because we require A and B are positive. Okay, so this is that. And then that means that omega is in the event that x plus b square greater than or equal to a plus b square. Okay, so every outcome in this event implies that this outcome in this event, so this event is bigger, right, than this event. Okay, so that this event is contained in this event. Okay, so this is bigger. So that's why the probability of this event is bigger than the probability of this event. Okay, now so we have that. And with this, so we are ready to apply Markov inequality, because for to apply Markov inequality, this must be a non-negative random variable, and this is a positive number. Okay, right. But before we apply Markov inequality, then we will say the random variable y. So we define y to be x plus b square is non-negative. Okay, and its expectation. Okay, so we compute its expectation. Okay, so that would be by the expansion. We know this is the second moment of x plus 2b of the first moment of x plus b square. Okay. Now, this is, and we know here, x is a random variable with zero mean, so this is 0. Okay, and the variance is sigma square. So when a random variable has zero mean, then its variance is equal to its second moment. So that this is become 2, the variance of x squared, and this is sigma square. Okay, so that we have sigma square plus b square. Okay, and of course, so it has finite mean. Okay, it has finite mean. So now by Markov inequality, okay, so by Markov inequality, we have the probability that x greater than or equal to a will be less than, would be less than or equal to here. The probability that y greater than or equal to a plus b square. Okay, and the expectation of y, and here is a plus b square here, and this is sigma square plus b square, and a plus b square for all b greater than 0. Very interesting, right? So this probability is upper bounded by this number, but this number is a function of b, because this is true for every b greater than 0. So now we can find out a b such that this ratio is minimized. Okay, it's minimized. Okay, and so so from here, so that we have probability of x greater than or equal to a is less than or equal to the increment of b greater than 0 of sigma square plus b square and a plus b square. Okay. All right. So we will evaluate this increment. Okay. So the increment is just the least upper bound, about the greatest upper bound. Sorry. No. Greatest lower bound. Okay. I'm sorry. So increment. Okay. All right. But you can use calculus because because b is greater than 0, so this actually is it's a differentiable function, infinite differentiable function. Okay, so so now I will not go through it by calculus. Okay. The upper bound. Okay. Sigma square plus b square, a plus b square is minimized. So you can think about this as a function. Okay. Okay, it's minimized. Okay, when b equal to sigma square divided by a. Okay. All right. So they are the way I think is quite standard. So for example, you take the first derivative of this function and let the first derivative to be 0 to find the local minimum or local maxima, right? And then try to see at each local minimum, local maxima, you now compute the second derivative to see if it's local minimum or local maxima. Right. And then, so you will see that what is the global minima. Okay. All right. And so you can determine that when b is equal to this number, if we achieve is a minimum. Okay, and so you will substitute to here. Okay, so that so when you substitute to the upper bound, okay, then you will find that the f of b when b is equal to this number becomes to the sigma square divided by sigma square plus a square. Okay. So that is the proof here. Okay. So the idea to prove the one-sided Chebyshev inequality is by introduce a degree of freedom b here. Okay. Introduce a degree of freedom So that for the same probability, we have a collection of upper bounds and with the degree of freedom b, so that the upper bound becomes to a function of b. That is the crucial point. Okay, and then try to find the minimum value of the upper bound function. Okay, and then to attain this upper bound. Okay. All right. So this is the one-sided Chev-Chev inequality, and this one-sided Chev-Chev inequality has a corollary. Okay. So again, it's one-sided Chev-Chev inequality. So we will remove the restriction that random variable x has 0 mean. Okay, so the x will be a random variable with mean, which is mu, and with mean and finite. Okay, they are all finite. Okay, with finite mean and finite variance, sigma square. Okay, then for all a greater than 0, okay, the tail probability has two kinds of tail probability. X greater than, so x minus mu greater than a, okay, is less than equal to sigma square plus a square. Okay, the other x minus mu or greater than equal to a, less than equal to minus a. Okay, so this is the tail distribution on the left hand side. Okay, and this is tail distribution on the right hand side. Okay, and we're upper bounded by the same number. Okay, same number here, the same number. Okay, so the proof. So we let y to be x minus u and z to be mu minus x. Okay, so we have these two. Then expectation of y is 0. And the second moment, okay, it's so this is the variance of, and the variance of y, which is just the second moment of y, because it has 0 mean, and this is expectation of x minus mu square, and so this is the variance of x here. Okay. Also, the expectation of z is also 0, and the variance of z, okay, because 0, so this is expectation of this square, the second moment, and the expectation of mu minus x square, but this is exactly this expectation, and again, this is the variance of x here. So you can see y and z both have zero mean and have the same variance sigma square. So now we are able to apply the one-sided Chebyshev inequality. So by proposition 8.5.1, okay, so we have that probability of y, so that x minus mu greater than equal to a for all a greater than 0. This is probability y greater than equal to a. Okay, so this will be less than equal to the variance of y. Okay, but the variance of y is sigma square. So sigma square plus a square. So that is the first one. How about the second one? That x minus mu greater than, less than or equal to minus a. Okay, and this is if we multiply minus 1 on both sides. So this is because mu minus x greater than or equal to a. All right. So this is probability of z greater than or equal to a. Okay. And again, by proposition 8.5.1, and this is the sigma square, because sigma square is also the variance of z. Okay. And we have done immediately. Okay, so we have the result here. So this corollary is a direct application of the proposition. Okay, 8.5.1 here. Okay, and next, then the next proposition gives another inequality. Called the Chernoff bound. Okay, so now x is a random variable with moment generating okay, so x is a random variable. All right, just saying that. All right, and the m of t is the moment generating function of x. Okay? The moment generating function of x. Now, if m of t exists, so if m of t exists in 0 to epsilon, or maybe not that necessary, 0 to, okay, some, I use B, okay, B here. For some b greater than 0, right? So if we know the moment genuine function exists for t is in a right neighborhood of 0, okay? Then for all a in R, okay? So now a can be arbitrary real number. Then the probability, the tail probability, okay, x greater than or equal to a, so a can be any real number, is upper bounded by the increment, okay, for t in 0b, such that e to the ta right, almost run out of the battery. Okay. All right. So so the upper bound will be, because that we will derive an upper bound for this probability as a function of t. Okay. When t is in this interval, all right, when t is positive, right, from 0 to b. The other thing is that if m of t exists in minus b to 0, so for t in from minus b to 0, for some b greater than 0, then for all a in R, the probability that x less than or equal to a, okay, so this is the left tail probability will be upper bounded by the increment of t is in minus b to 0, okay, and again e to the minus ta, okay, and the mt. Okay. Okay, so if m of t exists in both this interval or this interval, then we have both bound. Okay. Okay, so let's go to a proof here. Now, the first part. For any t greater than 0 such that m of t exists. Okay. We have that probability that x greater than or equal to a. Okay. And when we multiple t on both sides, because t is positive, so we will not change the direction of the inequality, right? All right. In that case, then we apply the exponential function. Okay, the exponential function. Because exponential function is a one-to-one function, and it's monotone increasing, right? So when we apply the exponential function, the direction of the inequality will remain to that. And since the exponential function, right, it's monotone. It's strictly monotone. Okay, so it's strictly monotone function, right? Maybe I will say strictly increasing. Okay, so strictly increasing function, so that it will preserve the direction of the inequality, and for a strictly increasing function, it is one-to-one, right? So the exponential function is one-to-one. So we have that. So these two events, so this event, they are all the same. Okay, so they are the same event. But with this transformation, then we know that this is a non-negative. So this is a non-negative random variable, right? And this one is a positive number, right? So this one is a non-negative random variable, and this one is a positive number. So we can apply what? We can apply Markov inequality, right? So the expectation of ETX here and ETA. Okay, this one. So this is from the Markov inequality. Okay. All right. So this upper bound is valid for any t greater than 0, such that m of t exists. M of t exists here. Okay. And this upper bound is a function of t. So that the probability of x greater than or equal to a will be less than or equal to the infinite, the greatest lower bound of this function for all t in 0 to b, because we assume that the moment generating function exists in this interval. Okay. Okay. And so here is e minus ta, and the expectation of. So this is just the moment generating function of x. Okay, so this is the first statement. Now we look at the second one. The proof is similar. So for any t less than 0, such that m of t exists, right? Then we have we have that the probability that x less than equal to a. By the way, we have for all a in R. So a can be any real number. Similarly, for all a in R, right? The probability of this event now is equal to, so if we multiply a negative t on both sides, we have to change the direction of the inequality. Okay? So this, we have to change the direction here. And once again, we apply the exponential function. And again, the exponential function is a strictly increasing function. Okay? So that the direction of the inequality will be reserved. Okay, and so now by Markov inequality, again, right? So this is a Markov inequality. So the upper bound is a function of t, right? For t less than 0. But in here, we know the moment genuine function exists. Okay? Exists in here, in this. Right? So the moment genuine function, this expectation is finite. It means this expectation is finite. Okay. So this is okay. So that this one exists for all t in minus b to 0. Okay, so I have to say here again m of t, eta, and this one exists for t in 0 to b. Okay. Okay, so that we have a finite expectation of this exponential function of x. So that m of t, okay, is finite. Okay, for all t in this interval. Similarly, m of t, by our assumption, m of t is finite for all t in this. Okay, this interval. So that will be then upper bounded by the increment t in minus b to 0 and e minus ta and m of t. Okay, so this is the Chernov bound. Okay, to apply Chernov bound, you have to know the moment generating function of random variable x. Okay, so without further information of the moment generating function, we can't find the increment, right? Because that, but you can see moment generating function is a nice function. So that in principle that you can find the increment of this function of t. Okay, without difficulty. All right, so we will introduce the last inequality, and now we have to prepare for something. Okay, so a real valued function f of x defined on an interval I of the real line is called convex if we have the following inequality. If f of lambda x2 or x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. For all x1, x2 in the interval, and for all lambda in between 0 and 1. Okay? All right, so geometry, if we write down here, okay, so this is a convex function. Right? Right. Suppose that the interval is from, say, A to B. Okay. And you pick up 2 points on the interval. So here you have pick up x1 here, x2 here. Okay? And now for each lambda in between 0 and 1, this linear combination is just any point in between these two endpoints. So that this linear combination is any point in the 9 segment and join x1 and x2. Okay, so for example, specifically, this is a lambda x1 plus 1 minus lambda x2. Okay, so this is in x1, x2. Okay, so this point is in this interval, in this 9 segment. And if lambda is equal to 1, then this point is just x1. If lambda equal to 0, then this is the endpoint x2. Okay. All right. Now the corresponding value here. So okay, so we go over here. All right. So this is f over x2, and go over here. So this here is f over x1. Go over here. This is f of lambda x1 plus 1 minus lambda x2 here. Okay? So this is okay. Now, if we join these 2 points, so we have 2 points here. So this point is x2, f of x2, and this point is x1, f of x1, and we join them. Okay, if we join them here. Okay, All right, and then we go. So, so the okay, this is, we go to here. So this point, okay, and go over, okay. Oh, sorry, not here. This is too smooth. It's hard to. Okay, I'll try. Sorry. It's a bad choice because maybe I redraw the diagram. Sorry about that. Okay, so here. Okay, and this is A, this is B. Okay, and we select point here, x2. We select maybe here, x1. Okay, so go to here. So this point is x2, f x2, and go here. So this point, x1, f of x1. Okay. And we select a point in between them. So for example, say here. Okay. So this is x is equal to lambda x1 plus 1 minus lambda x2. Okay. And this is in the line segment join x1 and x2. Great. Okay. All right, and the point here. Okay, so this is f. This is x and f of x. Okay. Now, when we join these 2 points, okay, join these 2 points here. Okay. Now, and we straight up. So here, okay. So this one here corresponding to this one, it's so here is f of x2, and this is f of x1, and here is f of x here. Now, but this point would be lambda f of x1 plus 1 minus lambda f of x2. Okay. The reason is that by the proportionality of so So you see that the ratio, okay, so when you go over, okay, so when you look at this triangle, okay, this triangle, so you can see that this is the ratio between these two segments is the same as the ratio between this segment. Okay, and so the ratio between two, so when you look at this bigger one, right, then the ratio between these two line segments is the same as the ratio between these two line segments. All right, so the ratio between these two, because the length of this line segment is the same as the length of this line segment. The length of this line segment is the same as this line segment, so that the ratio between this line segment and this line segment is the same as the ratio that. So that's why they share the same coefficients here. Just like this point is lambda x1 plus 1 minus lambda x2, because this is the two endpoints in the x-axis. But in the y-axis, the two endpoints is fx1 and fx2. So with the same ratio, you get the point here is lambda fx1 plus 1 minus lambda times fx2 here. But because it's convex, so you see that this point is higher than the function value f of x here. Okay, so that this because of the chord is higher than the curve itself. Okay, you can see this curve, so that this point is higher than this point. Okay, so this rate point is bigger than the orange point here. Okay, that's why. So this is the rate point here. Okay, and here is the orange point here. So you see that this is the upper bound. All right. So this is if we explain the convexity with this diagram, this is the idea. So to see that this is a convex function. Okay. But algebraically, convexity is expressed by this inequality. Okay. But as I explained in this diagram, that you can visualize the convexity from this diagram. Okay, and a convex function f of x on an interval is called strictly convex if for x1 not equal to x2, so if these 2 points are different, then the equality here hold if only if lambda equal to 0 or lambda equal to 1. All right, so equality only hold at the two endpoints, because if lambda equal to 1, then this is f of x1 equal to f of x1. If lambda equal to 0, then f of x2 is equal to f of x2. Okay, so this always true, right? But if a lambda is in between 0 and 1, all right, not equal to 0, not equal to 1, then the inequality is strict, all right. So that's why we call such a convex function to be strictly convex. Okay, and examples, right? First of all, the linear function, okay, the square function, the absolute function, exponential function, okay, is convex on R. All right, so these nice functions, ordinary functions, are convex functions on R. And in these functions, we know that these two are strictly convex. But these two are not. Okay? These two are not. Second, the x and the natural logarithm of x, and also the minus 1 over n, okay, on non-negative interval from 0 to infinity. Okay, from 0 to infinity. This is defined at 0, even though this is not, because that the logarithm of x at the 0 would be minus infinity, right? But because x is 0, so and x is go to 0 faster than this one. So we know that as n goes to 0, this one goes to 0. Okay, so that's why this function is well defined at 0. Okay, even though the logarithm of x does not define at 0. Okay, but this function is actually defined at 0. Okay, and these functions are are convex on 0 to infinity. Okay, convex, and they are actually strictly convex. Maybe I will just say strictly. Okay, strictly convex here. Strictly. Okay. Now, to have a convex function, then we will have concave function. So a real value function on an interval I, okay, of the real line is called concave if if f of lambda x1 plus 1 minus lambda x2, right, if this function value is greater than or equal to the linear combination of the function value for all x1, x2 in I, and for all lambda from 0 to 1, Okay, so we change the direction. Okay, for convexity, the direction is in this there, and for concavity, we change the direction. So it's the okay. So if we okay, for example, this is a famous okay, the 1/n function. And for 1/n function, you can see that if you join, okay, you find the code, then you will see that x1, x2, so and you have x here, two. So you go over to here, okay, and but at this point in the line segment, this one is lambda f of x1 plus 1 minus lambda f of x2. But this point, the orange point, is f of lambda x1 plus 1 minus lambda x2. Okay, so you can see orange one is higher, then it's bigger than the red one. Okay, this is the red color, this is orange color. Okay, so for a concave function, you will have this behavior. Okay, so this is called a concave function. And then once again, a concave function on an interval I is called strictly concave if for x1 not equal to x2, equality holds if and only if lambda equal to 0 or lambda equal to 1. Okay. Okay. All right, so we have a parallel definition for concave functions compared with the convex function. And convex function and concave function are closely related to each other. So f is strictly just convex if and only if you put a minus sign there. If only if minus f is strictly concave. So that's why you see in here minus, because this function is concave. But if you put minus sign here, then it becomes convex. Okay, convex here. So you have that. Okay, and an important property of convex function, of course, and also concave function is will be stated in the following lemma. So lemma 8.5.8. If f is convex on an interval I, then f is continuous on I. Okay, so any convex function is a continuous function, and of course, any concave function is a continuous function. Okay. So the proof will be omitted. Okay, you can refer to many textbooks to see it. So if x is a random variable and taking value in an interval I, and f is convex, okay, or concave, that's fine, on I. So suppose x is a random variable taking values in an interval I. And now f is a concave or convex function on I, right? Then a function of x, okay, this composition is also a random variable, okay? By proposition, we know in 5.7, I forgot something, okay, but all right, so by a proposition, I forgot the number, by a proposition in chapter, we mentioned that, chapter 5, okay. All right, so it will be safe, right? If we consider data processing by using a convex or concave function, okay? If the value of the random variable is on the interval where the convex or concave function is defined, right? So that would be no problem with that, right? And okay, so this is a very good application of this lemma. Another interesting observation is that if x is a random variable, right? Taking value in an interval, okay, and this random variable has a finite expectation, okay, E of x, right? Then the expectation must be also in I. Okay, so we name this interval to be I. So okay, and the proof will be an exercise. Okay, so you can do it by yourself. And actually, at the first section of chapter 7, we mentioned a result, right? We mentioned a result. Okay, so you can go back to check a simple fact about that, and that say that a random variable has taken value in a cross interval from A to B. Okay, then the expectation of x will be in between A and B. Okay, so we have shown that fact before. Okay, and but you can extend it to arbitrary intervals. Okay, arbitrary intervals I. Okay, can be open interval, can be infinite interval. Okay, anyway, so that you can follow the same similar proof. Okay, to show this fact, right? So anyway, so if x is a random variable taking value in an interval I, and if x has finite expectation, then this expectation should be in I. Okay, should be in I. Okay. Great. Another interesting factor from calculus is that how do we identify a function to be convex or concave? Okay, so we know a result. So suppose we have a function, okay, which is twice differentiable. Okay, so it's a twice differentiable real valued function, okay, on an interval I, okay, of the real line. Right, so we have a function which is twice differentiable. Now, if the double derivative, okay, the second derivative of f evaluated on all x, and which is greater than or equal to 0, or always greater than 0 over I. Okay, so if this is true, okay, then the f of x is convex or strictly convex on I. Okay, so we know that. Of course, if you change the direction, okay, then this becomes to concave. Okay, this becomes to concave. Okay. A simple proof is by Taylor's expansion. So, I'll give a simple proof. A Taylor series expansion of f of x around x0 around n x0 in I. Okay, so because f of x is twice differentiable over the whole interval. Okay, so we have a Taylor series expansion, all right, around an x0. So we can select an x0. So this is f of x0, and the first derivative of f evaluated at x0 times the linear term plus 2 to the second derivative evaluated somewhere, all right, and times the square term. And here, x star. What is x star? Okay, so this is for all x in I, where x star, all right, lies between x0 and the x. All right. So that it's between x0 and x, so that x star must be in I, in the interval, of course. Okay. So this is the Taylor series expansion of f of x. So this Taylor series is so we have this expansion because f of x is twice differentiable on the whole interval. Okay, on the whole interval. All right. So that we have this one. Okay. Now, because the second derivative will be non-negative, right? For all points on the interval. So this is always non-negative. And the second term, this term is a square term, so it's non-negative. So this term is non-negative. So if we remove this term, this one would become to a lower bound. Okay. So f of x would be greater than or equal to f of x0 plus f from x0. Okay. Times x minus x0. So we have that. Okay, for all x in I. Okay, so we have this general result. Okay, for this general result. If we have if this is strict inequality, then of course that this is strict, right? For all x not equal to x0. Okay? So okay, so this is it become to be strict inequality for all x not equal to 0. Okay, and for all x in I but not equal to 0. So we have to say for all x in I and x not equal to 0. Okay. Anyway, now we consider any 2 points, x1, x2 in I. Okay, and in this case, relating x0 to be in between x1 and x2. Okay, for lambda x in 0, 1. Okay, so x0 can be anything. So we select x0 there, and so that all right. So letting x0 is this one, and x to be x1. Okay, because we want to apply this inequality. So we have f of x1 greater than or equal to f of x0 plus f prime x0. Okay, f prime x0, and x minus x0. So you know this is x1 minus x0 here. And then you plug into x0 with this one. So you find that this is actually f of x0 plus f prime x0 and 1 minus lambda x1 minus x2. Okay, right? So you do substitutions, right, in here. Then the difference becomes to this one. Okay? And similarly, letting x0 equal to lambda x1 plus the same, right? 1 minus lambda x2. And x equal to x2, we have, so this time x equal to x2. In here, so we have fx2 greater than equal to f of x0 plus f prime x0 and the x2 minus x0. But the difference, when you do the substitution, you find that this is equal to f prime 0, and here is lambda x2 minus x1. Okay, so you have these two inequality. All right, and then you combine. Then you combine these two. So you multiply lambda with fx1 plus 1 minus lambda multiplied with f of x2 here. So that the lower bound is here will be lambda f of x0, okay, plus f prime fx0 and 1 minus lambda and fx1 minus x2, okay, plus 1 minus lambda. Here is f of x0 plus f prime x0 and the lambda x2 minus x1 here. But when you look at the term, you multiply lambda here, you multiply 1 minus lambda here, and look at this term. They will cancel each other, right? Okay, so they will cancel each other, and then okay, so this is becomes to okay, f of x0, okay, because that's the second term cancelled. So you have, and this is f of lambda x1 plus 1 minus lambda x2. So you prove the inequality, okay. And f of x, so f of x is convex. Okay. So now if f double prime x is positive, okay, over I, then we go through here. Positive, so this becomes 2 greater than that, okay. Okay, so we know that we have f of x will greater than f of x0 plus f prime f of 0, x minus x0 for all x in I, and x is not equal to x0. Okay? So that lambda f of x1 plus 1 minus lambda f of x2 would be greater than lambda. Okay. F of x is 0 plus f prime x is 0, 1 minus lambda, x1 minus x2 plus 1 minus lambda, f of x0 plus f prime x0, lambda x2 minus x1. Okay. And this is equal to f of x0. Okay. And this is f of lambda x1 plus 1 minus lambda x2. For lambda, right? For lambda is from between 0 and 1, but not equal to any of the two ending points. Okay. And x1 not equal to x2. Okay. So we have these inequalities. All right. So that's for, okay, and so the inequality is that we have to say that lambda not equal to 0. Okay. And yep, because if lambda not equal to 1, okay, because if lambda equal to 1, then x0 is equal to x1. So this is not, so this become to equality. All right. And for here, and for all lambda not equal to 0. Okay. Okay, so we have this one. In this case, and then f of x is strictly convex. Okay. All right. So we prove that this lemma. Okay, it's lemma. And a remark here is that the converse is also true, right? So I just remark the converse of lemma A.5 point B is also true, i.e. if a twice differentiable real valued, right? So if a twice differentiable real valued function twice differentiable real valued function f of x is convex or strictly convex on I, then the second derivative of f will be greater than or equal to 0 for all x in over I, or greater than 0 over I. Okay. Okay. So we have if a non-negative condition. Okay. Okay, and so now we are able to state the last inequality called the Jensen's inequality. the Jensen equality says that suppose x is a random variable, taking value in an interval I, okay, of the real line. And have, right? And having a finite expectation. Ex. And from our previous discussion, this finite expectation E of x must be a point in this interval I. Okay. And we have a function which is a convex function. Okay, on I. Right, which is a function on I. Such that the new random variable f of x has a finite expectation. Okay, so E of f of x. Okay, right. So the assumption here is that x is a random variable and taking value in an interval I, right? And having a finite expectation E of x. And we consider data processing function f of x, and this data processing function is a convex function, such that f of x, as we know, because for any convex function on I is continuous on I, so that f of x is a well-defined random variable. And so this random variable, we also assume this random variable has finite expectation. Okay. Then we have the bound here. The function of the expectation of x, okay, will be upper bounded by the expectation of this new random variable. Okay? And moreover, if f is strictly convex, okay, in this case, the equality, okay, the equality holds if and only if x is equal to its expectation with probability 1. Okay, means that if x is a constant, i.e. x is a constant with probability 1. Okay, so this is the Jensen's inequality. The Jensen's inequality here. Okay. Okay, and here we will give a proof, right? When the convex function, right? When the convex function f of x is twice differentiable on I. Okay? Of course, the Jensen equality always true for any complex function. Okay, but to give a easy proof, we first assume that the complex function is twice differentiable. Okay, so here is a proof with that assumption. So now, because the complex function is twice differentiable, so by Taylor's expansion, by Taylor's series expansion, okay, Taylor's expansion of f of x about x equal to the mu, about the expectation. Okay, we have, so we select x0 to be a mu. So we have f of x is equal to f of mu plus f prime mu x minus mu plus f double prime epsilon psi, okay, the psi and x minus mu square divided by 2, okay, for all x in I, okay, and where the psi is some value between x and the mu. Okay, so we have that because we expand this complex function about the mu. Okay, about the mu here. Now, since the second derivative always greater than or equal to 0 for every psi, so we have this inequality that f of x would be greater than equal to f of mu plus f prime mu x minus mu. Okay? So we have this one. Okay? So this function is greater than this function for all x in I. Okay? So that when we plug in the random variable here, so that this random variable will be f mu plus f prime mu x minus mu. Okay, so we have this random variable is greater than equal to this random variable here. Okay, so now we have a random variable greater than equal to another random variable, and both of them. Okay, so both things, expectation of x and expectation of f mu plus f prime mu x minus mu. Okay, this is 0, right? You can, no, this is equal to f mu by linearity, so this is 0. So they are finite. Okay. Okay. So so by a proposition in chapter 7, okay, I think I can find that that proposition number. I think okay, so it will be by proposition 7.4.8, the second statement. Okay, yeah. So that the expectation of f of x would be greater than or equal to the expectation of the right hand side so which is f of u, so which is f of expectation. Okay, so this is exactly the Jensen's inequality. Okay, we want. Okay, so the expectation of f of x is greater than or equal to the function of the expectation. Okay. Okay. So and you can see that so if f is strictly convex, okay, if x is strictly convex, okay, so if f is strictly convex, then so you can see that we know the lemma says that. So we have so that the double, so this we know that f double prime psi is equal to 0. So we have f of x will be greater than f of u plus f prime u and the x minus u for all x in I, and x is not equal to u. Okay? Okay, so that f of x greater than f of e plus f prime u and x minus u for all okay, so I will now this time f x of omega for all x of omega and for all omega and x, but and x omega not equal to mu. Okay, so we have this inequality. Okay, so that's equality holds if and only if. So if only if that that the probability that x not equal to mu is 0. Okay, and if only if the probability that x equal to mu is 1. If only if x is equal to its expectation with probability 1. Okay, so that is the end of the proof. Okay. Okay, so I finish chapter 8, and so now I complete all the material in this semester. Okay, so I wish you good luck in the final examination.